iodine, it will form diborane and sodium iodide and also hydrogen gas. Boron is used to dope silicon and germanium semiconductors, modifying their electrical properties. Aluminium is used in transportation like automobiles, aircraft, trucks, railway cars, marine vessels and bicycles, etc. Hello everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today I am going to start session 3 from the chapter Some P block elements. In the last session we have discussed about physical and chemical properties, anomalous behavior of boron, important compounds of boron. These are the 3 contents we have discussed in the previous session. In this session we will discuss about diborane, its preparation, methods of preparation, uses of boron and aluminium and its compounds, and also we will discuss about some of the introductory points of carbon family elements. Methods of preparation. Diborane is prepared by treating boron trifluoride with lithium aluminium hydride in dimethyl ether. When boron trifluoride is treating with lithium aluminium hydride in dimethyl ether, it will form diborane and lithium aluminium fluoride. This is our main product. In industrial method, the industrial synthesis involves the reduction of boron trifluoride by sodium hydride. When boron trifluoride is treated for reduction with sodium hydride, it will form diborane and sodium fluoride. In laboratory method, a convenient laboratory method for the preparation of diborane involves the oxidation of sodium borohydride with iodine. When sodium borohydride reacts with iodine, it will form diborane and sodium iodide and also hydrogen gas. These are the 3 methods in which diborane can be prepared. Physical and chemical properties of diborane. Diborane is a colorless gas at room temperature with the repulsive sweet odor. Odor means smell. It is having sweet odor and which is a colorless gas. It is highly toxic with a boiling point of 180 Kelvin. That gas is completely highly toxic, which is not good for our body, and also it's having boiling point of 180 Kelvin. Diborane catches fire spontaneously upon exposure to air. When it has treated to air, it will catches fire spontaneously. Diborane will ignite spontaneously in moist air at room temperature. It can ignite spontaneously in moist air also for the room temperature. And the chemical properties, reaction with air, it burns in oxygen with the liberation of large amount of heat. What they have told, diborane will catch fire spontaneously when treated with air. Air is nothing but oxygen. When diborane is treated with oxygen, it will catches fire with the enormous of heat. See here, minus 1976 kilojoule per mole, that much enthalpy is needed. Reaction with water, boranes are readily hydrolyzed by water to give boric acid. When boranes are treated with water, it will catches and it will get hydrolyzed to form boric acid and liberation of hydrogen gas. Next, reaction with ammonia. The direct reaction of ammonia which gives diborane, which is formulated as NH3 2BH2 plus and BH4 minus. It is having both cationic and anionic species. Further heating gives borazine, means B3N3H6, called inorganic benzene due to its ring structure. Okay. See here, when diborane is reacted with ammonia, it will form cationic and anionic species as an intermediate. Further heating, it will give borazine, which will be considered as inorganic benzene due to its ring structure. Also, it will liberate hydrogen gas. Diborane undergoes cleavage reactions with Lewis bases to give borane adducts. See, it will form borane adducts when the cleavage reaction will takes place. Next, structure of diborane. The 4 terminal hydrogen atoms and 2 boron atoms lie in one plane. Above and below this plane, their bridge hydrogen atoms can be seen. 4 terminal hydrogens is on the plane and 2 hydrogens are bridged hydrogen atoms. Each boron atom forms 4 bonds even though it has only 3 electrons. The terminal boron and hydrogen bonds are regular bonds, but the bridge boron hydrogen bonds are different. Boron is having 3 electrons, but also it will form 4 bonds. These 2 terminal hydrogens are common, but the bridge hydrogens will be rare. Each bridge hydrogen is bonded to the 2 boron atoms only by sharing of 2 electrons. Each bridge hydrogen will be formed by sharing up of electrons. Such covalent bond is called 3-center electron pair bond or a multi-center bond or banana bond. This sharing of electron, how it will be seen? Like this. So, it will be called as 3-center electron pair bond or multi-center bond or banana bond. This banana bond could be seen only in diborane's structure. See here how it will be formed. Next, uses of boron and its compounds. Boron is used to dope silicon and germanium semiconductors, modifying their electrical properties. Doping means, in physics concept, the introducing of impurities in the intrinsic semiconductors. So that is called doping. For that, boron will be used. And boron oxide is used glass making and ceramics. Ceramics, you know, in the laboratories which we will use, china dish and all. Borax is used in making fiberglass as a cleansing fluid and water softener, insecticide, herbicide and disinfectant. Majorly pesticide or insecticides, borax will be used. Boric acid is used as mild antiseptic and as a flame retardant. Boric acid is used as mild antiseptic, not to get infected, that antiseptic. Flame retardant means, we know boron is having, which will be reacted towards air with a enormous amount of heat. So, flame retardant means it will ignite flame continuously. Boron nitride has better thermal and chemical stability. Hence, boron nitride ceramics are used in high temperature equipment. So, it is very high resistant properties are there. So, this boron nitride will be used in the materials or in the equipments which will be holding the capacity of high temperatures. Boron carbide is used in tank armor and bulletproof vest. Okay, in bulletproofs, also in tank armors, it will be boron carbide will be used. Next, uses of aluminium and its compounds. Aluminium is used in transportation like automobiles, aircraft, trucks, railway, cars, marine vessels and bicycles, etc. Aluminium is a metal, you know that, which will be used many automobiles or transportation industries. Next, packaging, cans, foil, etc. You have seen that oil cans and all, it will be aluminium cans. Alum is used in water treatment, that aluminium alum will be used in water treatment. Next, construction, windows, doors, sliding, building wire, etc. Cooking utensils, electrical transmission lines for power distribution, alnico magnets, super purity aluminium used in electronics and CDs. Powdered aluminium is used in paint and pyrotechnics such as solid rocket fuels and thermite. Alloys like magnesium, duralumin also can be used. Usually this aluminium will be used in mainly in daily life. So you can observe in the uses of aluminium. Next, carbon family elements. Till now we have seen group 13 elements and its anomalous properties in boron, and now we are moving to group 14, that is carbon family elements. The carbon family consists of one non-metal, 2 metalloids and 2 metals. One non-metal is carbon, 2 metalloids silicon and germanium, 2 metals tin and lead. Metalloids means, you know, it is having the behavior of both metallic and non-metallic nature. Carbon family elements contain atoms that have 4 electrons in their outer energy level. It is having 4 valence electrons. The carbon family elements have widely variable physical and chemical properties. The carbon family elements tend to be fairly unreactive. It is unreactive in nature, means a little bit stable. The elements tend to form covalent compounds. Covalent means sharing up of electrons, by that covalent bonds will form, which will exhibit the covalent bonding nature, which called covalent compounds. Though tin and lead also form ionic compounds. Tin and lead will form ionic compounds, but other than that will form covalent compounds. Carbon family elements exist free in nature and in compounds. It will be free in nature. Occurrence. Carbon is the 17th most abundant element by mass in the Earth's crust. It is the 17th most available element in the Earth crust, and it is widely distributed in nature in free as well as in the combined state. Carbon usually will be in free state, you know about gas also, and also in combined state also. In elemental state, it is available as coal, graphite and diamond. And in combined state, it is present as metal carbonates, hydrocarbons and carbon dioxide gas. It is available in coal, graphite, diamond also. It is available as metal carbonates, hydrocarbons and carbon dioxide also. But that percentage is very less, 0.03% in air. Naturally occurring carbon contains two stable isotopes. Isotopes means that atomic number will be same, mass number will be different. See here, carbon 12 and carbon 13 isotopes can be seen, two stable isotopes. In addition to these, third isotope carbon 14 is also present. It is radioactive isotope with half-life 5770 years, used for radiocarbon dating. Silicon is the second, 27.7% by mass, most abundant element on the earth crust and present in nature, form silica and silicates. Next, germanium exists only in traces. Next, tin occurs mainly as cassiterite and tin oxide and lead as galena, that is lead sulfide. Ultra pure form of germanium and silicon are used to make transistors and semiconductor devices. Both tin and lead are generally unreactive metals. Tin has two common allotropes. At room temperature, the stable form is white tin. Below 286.2 Kelvin, the stable form is grey tin. Tin has a tendency to displace lead and not vice versa. It is having the capacity to displace with lead, tin to lead, but not lead by tin. Okay, these are the occurrence. Carbon will be existed as free and combined state. It is having three allotropes, carbon 12, carbon 13, carbon 14, but most stable carbon 12 and 13, carbon 14 very radioactive, and germanium will be seen in traces, silicon as silicates and silicons, silica and silicons, tin as a cassiterite, and lead cannot be replaced by tin, but tin has a tendency to displace the lead. Next, properties of carbon family. Electronic configuration. The valence shell electronic configuration of these elements NH2NP2. If you see carbon 6 atomic number 1s2, 2s2 and 2p2. This 4 electrons can be seen. The inner core of electronic configuration of these elements in this group also differs. In between it will differ. Next, covalent radii. The covalent radius increases from carbon to silicon. From silicon to lead, a small increase in radius is observed. This is due to the presence of completely filled D and F orbitals in heavier members. From carbon to silicon, the covalent radius will be increases, but from silicon to lead, a small increase can be observed, because here the D and F orbitals will be interfered in the heavier elements, so it can be little bit observed. Next, ionization enthalpy. The first ionization enthalpy of group 14 members is higher than the corresponding members of group due to the influence of inner core electrons. In general, the ionization enthalpies decreases down the group. The first ionization enthalpy of group 14 is higher because of influence of inner core D and F electrons. The ionization enthalpy will decreases down the group. Small decrease in ionization enthalpy from silicon to germanium to tin and slight increases in ionization enthalpy from tin to lead is due to the poor shielding effect of intervening D and F orbitals and increase in size of the atom. Here, poor shielding effect can be seen due to the D and F orbitals. Next, electronegativity. The electronegativity of carbon family elements are slightly more than group 13 elements due to their small size and the electronegativity values for elements from silicon to lead are almost same. Silicon to lead, you cannot observe the as usual trend because there is a d and f orbitals are present. That's why other than tin and lead, silicon and lead, you can observe as usual trending, that is from left to right. The electronegativity will increase because the atomic size will decrease. This is about atomic properties of carbon family. In the next session, we will discuss about physical and chemical properties of carbon family, anomalous behavior of carbon, allotropic forms of carbon also could be seen in next session. I hope you have understood completely whatever I have taught today. We'll meet in the next session. Thank you.